Okay, he's gone. For context, Swix is at the DMV. He is in the process of getting his license. So he's out for this one. But let's give it a few minutes for people to join in. And then we'll get started. These are pretty good papers.
No
We've
wonder
got
it was so stressed out, huh? To the DMV.
okay, so we'll give it a few minutes for people to join. Do we want to get a quick intro of what's going on?
O, przepraszam, tutaj. Tak. Dobrze. Więc trzymam. Tak, tutaj.
He's left and hasn't muted people upon entering. Let me fix real quick. Okay, so Raphael, you're kind of ready to present, share?
Yep, sure.
Perfect. Let's give it another 2 minutes. You want to do a quick intro?
Yeah, I'll start. So, I'm Raphael. I'm working mostly on the LLMs. I'm working to create LLM for Georgian language, which is a country in Europe, which is a low resource language. And yeah, we already developed our first model. We started like the zero data, zero compute, and zero talent because only a few people work on LLMs in Georgia. So we managed to develop the model, which like outperforms larger models like GPT and Claude for Georgian language. And also it's like for enterprise use cases, and it supports function calling, JSON structure mode, and RAG and so on. So if you want to test it, I can give you the free API. And yeah, that's
Very sick. Yeah, share info in Discord. I'm sure a lot of people are interested. I know Eugene Cha, he presents quite a bit. He's very interested in low resource language models. But yeah, so today we basically have the two S1 and scaling up test time compute papers. I'll let you go through them however you want. Chat normally gets pretty active, so if you're monitoring, that's cool. If something is very confusing, I'll probably interrupt, but take it as you want.
yeah, sure. Okay.
Actually, let's give it another minute. Some people are needing passcodes. They're just not using the right link. But
Okay.
once we hit 50, we should be good. Okay, we've got a new link posted. I think we're good to start.
Yeah. Can you see the screen?
Yep.
Okay, so today I want to cover two paper, but both of them are about the test time scaling and the latest hot topic. The idea is that we want to build LLM, which so we want to increase the performance. So we know from latest models like OpenAI, Gemini, and Anthropic already that reasoning works, the thinking works. So idea is we want to replicate that work, and this paper from Stanford is trying to replicate the reasoning step with only few $100 or something like that. So only a small budget. The idea is that. So they collected 1K samples in some way. I'll take in a bit. And yeah, idea is that they train QN 2.5 and it outperforms O1 preview actually on the mass and reasoning datasets. That's the idea, and they created some kind of technique which is pretty simple, I think. And yeah, mostly it's for the people like me who don't have a lot of budget and resources to train the model and still have ability to train reasoning LMs. So yeah, objective is to create a simplest approach to achieve space-time scaling, actually. So to deep dive into the methodology, scroll a bit. Yeah, the first thing is that they somehow created 1,000 examples. And what they did actually is to took some mass data sets like nominal mass, AGI eval, and so on. And they generated reasoning tracing using Gemini 2.2 flash thinking. And they did some pipeline after that. So first is that they collected almost like 60K examples. Then they filter it using the quality, which means to drop some examples based on the formatting, some ASCII errors, as I remember. And yeah, after that, they got 54K. And yeah, then they filter based on the difficulty. And what they did is that took two model, like I'm not sure if you can see the image perfectly, but they took two image QN 2.57B and 32B, and they asked the question on both models, and if any of the model responds correctly, they just filter those examples. So the idea is that they want to choose the hardest question that none of the model can answer. And they evaluate the correctness using the Claude 3.5 Sonnet. And after that, they got 25K samples. And also they took the length of the reasoning, so reasoning trace. So you can say that if the length is big, maybe it's a more like challenging problem or something like that. After that, the key point is to take some. So since the idea is we want to run and train the model and small samples, they have to take some sampling, right? So they took some LLM and clustered those examples, so 25K, and after this took some just do some sampling to collect 1K examples and took them based on the reasoning trace length, actually. So yeah, after those pipelines, they collected 1K examples, 1K data sets with replace like the question, the reasoning, and the answers. So if there are any questions about that, I can stop a few seconds and I can continue because it's important to understand that it's simplest approach, I mean, but yeah, it's pretty good to collect and yeah, took some data. Okay, after that, they trained the QN 2.572B, and yeah, as you can imagine, they got some good results. Second. So yeah, another thing that that I want to explain before I show the results is that after creating data set, they create some technique to increase the test time scaling. So the name is budget forcing or something like that, as I remember. And the idea is that if you want to generate more tokens and more thinking steps, you add the word weight in the output and model understand to continue the generation. And if you want to stop the thinking process and stop the generation, you add the final answer, those words in the generation, and it stops the process. Yeah, that's the budget forcing here. So they have the maximum number of tokens, the minimum number of tokens, and you have the ability to control the length of the traces based on those simple words. That's the idea. Yes. Okay. And about the results, the first thing is that it outperforms O1 preview, and yeah, also it's comparable to R1 distill from DeepSeek, QN reasoning, and also the Sky1T, which is a few weeks ago. Yeah. Also interesting thing that we can see is that if you increase the thinking time, so if you generate more tokens, the performance increased for some data sets like math and GPQA. Okay. What else? Yeah, that's the example if you want to see how it works. So let's say how many are in the Raspberry, and as you can see, it got the wrong answer. Then they add the word wait, which continues the generation, and after that it corrects yeah, return the correct answer. Okay. Yeah, another good thing is that uh, as you can see, after some time, the results converge. So if you generate a lot of tokens, or if you add a lot of weight words in the generation, after some times it converges. That's another result. And also they compare those methods for other methods like majority voting or other else, and found that the scaling law for the test times for those techniques are different. So as you can see, for this budget forcing, results goes up, but for majority voting, yeah, a little bit. Yeah. Else? Yeah, those also is an interesting results. So as you can see, this is their model, the final one, and they compare the results for OpenAI, Gemini, and QN, and other open weights and open data models. Also, I should mention that the data, the model, all of these are open source, so you can check it, yeah, and test. And then data as well. Okay, so yeah, as you can see, it outperforms for O1 preview on math dataset and for AME and not for GPQA, and the same results for O1 mini. For Gemini, we only have one result. For other two, as I remember, they can't test it because Gemini blocks some API requests. And for AME, this is only 30 or 40 examples, so they test it manually in a Google AI Studio, and that's why we have only those results, and it's nearly comparable to the Gemini. And the idea is that they kind of distill Gemini, right? And with only 1,000 example, they got comparable results to Gemini, actually. Another interesting thing is that this is the base model that they took, and yeah, the gain of the performance is a lot. So like 30 for AMI and so on, which is huge. Yeah, and some results from DeepSeek is comparable as well, but the idea that they mention is that in those cases they only took 1,000 examples. So for DeepSeek, they distill 800K examples to train their models. Okay. Okay. After that, they did some ablations and found some good, interesting things, I think. So first one is that how you choose 1,000 examples from 60K. And yeah, they choose like, for example, from random, from diverse, like based on the clusters, took the 1K based on the length of the traces and just train on the full data set. And as you can see, it outperforms all 1K examples, but it's comparable, and yeah, full data set outperforms a little bit. But the idea is that we only use 1K examples rather than the 60K, and got mostly the same results. Yeah, also.
I found that last section pretty interesting. Basically, these results show that if they didn't go through their like four-step approach of filtering to 1,000 samples, their results are 30% worse, right? So their whole thing of like step one, see if the questions are easy, step two, cluster and take like diverse samples, that alone to like get the 1,000 high quality versus just 1,000 random samples, 30% net difference. So pretty big importance in their little filtration pipeline.
Yeah, exactly. So the pipeline is pretty simple, I think, but maybe one of the good thing is to filter based on the quality and based on the model response, I think. Rather than that, like the formatting, I think doesn't matter actually. But
Yeah,
yeah,
the model response, if I'm not mistaken, from the two base Quen models was basically just throwing out a lot of it. So like when they used the Quen 7B and Quen 32B, the base models, basically what they did was they ran their 60,000 questions through these. If the two basic models could answer it correctly, then we just throw out the sample. It's too easy. So
yeah,
step one, that filters a good bit just to get hard questions. But yeah, high level, their whole pipeline was pretty interesting. Um,
yeah,
that seems to be like half of the value. So
yeah,
a lot of it was just, yeah, there's good at 1,000 samples. The other one was kind of the budget forcing, right? So
yeah.
you wanna, I think, explain a bit more about how the budget forcing is working and what it's doing? I thought it was pretty unique.
Yeah, just to summarize, those are the important things. So data sampling, those data pipeline, and budget forcing actually. For the data side, actually, I test this idea for my use cases, not for the reasoning thing, but I collect and I mix the data set based on this technique, and yeah, it really works because you can choose the high quality data based on that. And yeah, about the budget forcing, as I mentioned, so you can you have ability to control the size of the reasoning. So let's say you have the minimum number of tokens that you want to generate and maximum number of tokens that you want to generate, right? And you can control this the length based on the wording. So if you want to generate more, you add wording like weight, like as you can see here, and model continue the generation and generate more tokens. And you can do that several times, like 2 or 3 times if you want to generate more. And if you want to stop the generation, you can add the final answer word and it stops the generation. So you can control the maximum number of tokens based on that. Yeah, that's the idea. I'm
Yeah,
not
it's
sure
very
if
interesting.
any other work is doing something like that. Uh, but yeah, good.
So after this came out, some other people started doing it. Essentially, what people are also saying is it's a way. Some people are saying this is the distinction between O3 mini low and O3 mini high, and it allows you to
Yep.
control how much thinking you do, right? So as we generate tokens auto-regressively, eventually we generate an end of sentence token, end of text token, and then we stop generation. So what they're doing is anytime the model, the next likely token is the end of token, end of sentence, we replace it with a thinking token, So, what should I do? And like it continues thinking. And now at inference time, you can kind of just force more thinking, or if it's rambling too much, you can, force it to end once it's given an answer if you look at the outputs, or you can tell it, like final answer and start boxing your answer. But the interesting thing here is like, yeah, it also played quite in effect. So they show their scores of with and without budget forcing. But it's essentially like a inference time hack to control the amount of thinking, right? So if you think of like as an API consumer, if I want thinking to be like 30%, maybe I add in three extra think tokens instead of end of sentence. If I want like 60%, I add in six. Very high level just to understand conceptually what's going on. But that's kind of what the budget forcing here was. Um, Another comment RJ made is it only had a minor improvement over the base Quen model. It seems pretty high. Do you want to go to the performance benchmarks
You
again?
mean the base? Yeah, this is the base.
Base is pretty bad. So the
Yeah,
base AIME score of Quen 32B is 26.7. The
yes.
S1 score is 50 and 56 with budget forcing. So
Yeah, this is without and this is the with budget forcing. Yeah.
Oh,
yeah.
right. I was misreading. I was looking at the QWQ. Yeah, okay, got it.
Ah,
Yeah.
yeah.
QWQ is the Quen reasoning model preview. They haven't released it yet. I
Oh,
think they have a second update that they put out this week. Someone at the Quen team on Twitter is cooking about this and keeps saying he's doing it. But that's Quen's internal reasoning model. It's not just the base instruct. It's also just not out yet.
yeah.
But distinction.
Yeah, that's what surprised me that with only 1,000 example, you can just run fine tuning with SFT and got a really big improvement rather than the base model. That's yeah, good
Yeah,
result.
it's kind of it's not necessarily just fine-tuning with SFT, right? It's also distillation because they're distilling Gemini thinking traces. So it's not like a distillation loss, but it's SFT to match like Gemini's thinking output plus a little hack of think a little more if you're not on the right path. But the interesting thing there is still the 1000 samples does this very well with distillation. So QWQ is Quen's internal native RL-based reasoning model. And if we look at it, the performance is pretty similar, right? Like the model
Yeah.
is not out yet, but performance-wise, it's pretty much just as good. The difference here and with S1 is probably that, they're similar to the 800,000 samples. Like I don't think they
Yeah,
said, but I think it's a fair assumption that yeah, they're in the hundreds of thousands of samples.
yeah, exactly. And they just spent I don't remember 26 minutes for 16H100 to run the training.
Yeah, 1000 samples, not much, but it's very cool work to see. And then this
Yeah,
also leads to here's a rumor of here's what OpenAI does for more and less reasoning models, thinking models, and also here's a little hack for how you can do it.
yeah. And also they compare these budget forcing techniques for other conditional control techniques like token conditions, tab conditions, and class condition, which is like you say that let's think 100 words or something like that, or let's think with 3 steps. And yeah, they did some ablation and they took that budget forcing is the best rather than those techniques. Yeah. So. Also, they did ablations about the word actually. So they compare the keywords like wait and like alternative without string or something like that. And yeah, wait works the best. It's also interesting.
Yeah, some of the other little local stuff that has come out after this paper is instead of just appending the wait word or something, people started slapping in aha moments and like people themselves have started testing quite a bit of this, right? So instead of end of token, what they found best was to, give it wait, which is like, wait, I've figured this out. And it's like, that's pretty cool. Makes like it's an interesting idea. People locally have tried like 50 other things and like one thing I was helping someone on is let's train a classifier to see what's the best swap word to put in, and like it does slightly better, but now you have to run a classifier, but it's fun little stuff.
Yeah. So idea of this paper and motivation is that this is the simplest technique I think which gives you big improvement on in terms of results like rather than base model, yeah, mostly the same with Gemini and so on. And that's the main idea, I think.
Yeah.
Uh, yep. What else? I think
We
that's
have
it. It's a pretty small paper, but pretty interesting. And yeah, just
all the
maybe,
all the
yeah,
results are on math related data sets. I
yeah,
wonder if there's a certain deal of performance degradation on more
yeah,
other um, data sets that require reasoning but maybe are not math based.
yeah, that's a good question. But yeah, for this paper, they just only test on the math.
so
But
well, no,
that,
GPQA is not just math, and they go into their data set curation. The majority, like the 50,000 samples out of the 60,000 they started subsetting from that whole data set, they include quite a few other non-math based benchmarks. And then part of their clustering is to like not just sample math. So their Sonnet clustering does diversity past just math. So they have standardized like LSAT in there. They have the hardest questions of the LSAT. They have chem, bio, physics. They have other stuff in there. And then the GPQA benchmark shows that it's not just math. The other two are math, but at a high level, one thing that we've seen with reasoning models is like math and verified code kind of converge to quality on other just general tasks, but one of their benchmarks here is not math.
Yeah.
People, did you see, did anyone try replicating this with some of the same models that the R1 model was distilled to? Because I would be interested to see like, okay, if we use this technique versus distillation from like the R1 like God model, what happens? Like, how does that compare? Because it's a little bit apples to oranges to compare to like a distill, right? I
So
mean,
two
it's this
things.
R1 distill, but is that like the same size or like which one is that?
So R1, like DeepSeek themselves put out um Quen 32B R1, like Quen
Oh,
32B reasoning. So they did the exact same model. So
okay.
in the opposite sense, S1 did this on the same model that DeepSeek
Okay.
did it on. So
Yeah.
we have the direct two. I
Yeah.
think, and I could be completely wrong here, I don't think DeepSeek told us how much data they used for distillation. They just said we distilled the big ones. Here you go, they're good. Here's how they perform. But
Yeah.
like, we don't know. Did they do 500 samples? Did they do 50,000? We don't know what they did for distillation, except for I think they did a proper distillation loss, not just SFT on outputs.
Yeah.
And it's a little different too because like this is trained on outputs from Gemini. That would be on outputs of R1. So
Yeah.
like there's a little stuff different, but directly to your question, DeepSeek did do the same model. You
Okay.
can compare the two. And I don't know if someone wants to fact check or make a note. I don't think the DeepSeek paper said how many samples they used for their distillation.
Got it. Yeah. But is that result in this paper? Did anyone figure out is that the same? Is that R1 distill? Is that the like equivalent Quen model, the 32B? Because like regardless of how much, I mean, obviously it's like I mean, to me this is an amazing result, right? Like you use minimal compute and get something very close to the same performance. That even if it's not up to par, I'd just be curious to see how it compares.
So two things. One is I think what they're going after here is sample efficiency, right? So they want to show how you can do it in a couple thousand samples. And two, I think we can look at the R1 distill. So apparently R1 distill is better according to my quick let's ask ChatGPT, but it could have hallucinated. So yeah. I just threw it
Bias
in
too,
GPT
man.
and it's like R1 distill is better. I don't trust it. Okay, so it looks like they did give numbers. I remember this. So they used 600,000 SFT. Also, thanks Leah for pointing this out. So for the R1, the original DeepSeek paper, they used 800,000 samples, 600,000 SFT plus 200,000 reasoning traces. And I think they actually, yeah, they do put it in the paper here. So it performed, they have benchmarks of R1 distill right there. It's the third row. But sample efficiency, that's the difference.
But also the technical distillation was different, right? So they did the logics.
Yeah, totally not like totally get like it's going after something different. Just one, it's an interesting comparison. But I guess yeah, so that distill presumably is that 32B Quen.
Yes, it is. 800,000 samples.
Yeah. Okay. Um,
Cool. Do we want to move on to second paper or any other closing thoughts on this one? I'm sure if there's discussion in chat, we can always pop back in, but we have a second paper.
okay. Yeah, so the second paper is scaling up test and compute with latent reasoning, a recurrent depth approach. So the topic is the same. So we want to build a reasoning model, but the idea is that most of the model that we already know generates the reasoning and thinking tokens in the output, right? And in that paper, they create the architecture which doesn't produce explicitly tokens in the generation. So it thinks and reason in the architecture itself. That's the main difference. So Why do we need that kind of model? Because if you want to generate, like as you can see, the latest models like generate 1,000 tokens in their thinking and reasoning. So it takes a lot of time. Also, you need to have a big context window, and which doesn't work for small models. And also, as they mentioned, there are some reasoning abstractions that you can explicitly say by words. So you need to have some high dimensional latent space where the model reason and think itself in the architecture. Yeah, that's the idea. And about the methodology, so they create the architecture, so they add some recurrent block in the transformers. And the idea is that when you train the model, you run several times in the loop. So as I remember, they took random numbers. So sometimes you run 3 times, maybe 5 times, and so on. And yeah, that's the most of the idea. So they took a 3.5B model and they trained on 800 billion tokens. And as I mentioned, it is equivalent like 50 billion parameter models. So the result is pretty impressive as well. Yeah, and as you can see, the results in the first case, as you run the loops in the test time, so performance increase, and for some benchmarks, it converges quickly, but for GSM 8K, it has a lot of improvements actually. Okay. Yeah, so why they train the models, as I mentioned, that you don't in this case you don't need to have the specialized data for the training. Also, this technique takes less memory. So idea is that you use small models but more compute to increase the performance. And yeah, as I mentioned, it takes more flops, but it's more efficient. Since you have small models, you don't need to have a communication cost or interconnect, and it's much faster, as I mentioned. Yeah, that's the architecture. Yeah, there are some sections, the topics why they use the embeddings, and yeah, some improvements in the efficiency because they train this model on AMD hardware with specialized GPUs, as I remember, and as I mentioned, they needed to create some kind of tricks and to make some fast training. Yeah, so and as the previous paper, also they published pre-training codes and the model and data. Okay, so what they did actually is that since they don't have a lot of money, so they just took some already published data sets. They just create some kind of a mix, and yeah, mostly they wanted to test the model on math and reasoning tasks. So most of the data comes from the coding and math data sets. And as I mentioned, the mixing strategy maybe is not the best, but the idea is that just to test if this module architecture works. So yeah, yeah, they do some. They published the parameters, hyperparameters. They did some packing and so on. One of the problem that they have in the training was to since it's a different architecture, they mentioned that hyperparameters and the setup matters actually. So in the first run, this is the orange, and they don't have a good performance. But after some tweaking, like learning rate and some hyperparameters, they get some good results. The blue one, which is the latest, the main model, and yeah, loss goes down. And yeah, I'm not sure about the number of loops, but yeah, maybe we'll see in the results. And yeah, so when I see the results, it doesn't look very good rather than the previous paper, but we can see some improvements in the for loop, I think. So if you check the results, it doesn't outperform most of the models actually. So they compare the Olmo models and Pythia, which is pretty old, I think, already. And yeah, the result is not so good. But the main thing is that performance increase if you increase the loop as well. Yeah, as you can see, 49 and 69 for arc easy. Um, yeah, and um, yeah, they test on GSM rate K. Mhm. And yeah, also one thing is that they check if this architecture emerge some ability, like for example, a chain of thought and some skill that we know for the LLMs, right? So they test those ideas and see that this architecture works also for with the context. So if you give some, so for example, few short examples, it improves the performance. So just to test the idea that it doesn't goes wrong for other ability. Yeah, they published some early checkpoints as well. And yeah, as you can see, performance goes up. There was yeah, also they compare the baseline. So baseline needs to take the same data set and run just with the base training technique and without those architecture. And yeah, as you can see, performance is much better as well. So for example, 46 and 69. I think this is the good result because we know that with the same data set, with the same compute, let's say, you get much better performance. And also they compare with R equals 1. And yeah, actually it's the less performance than the baseline. That's another interesting thing as well. Yeah, they checked a few shot examples, and as you can see, if you use the zero shot, it converges quickly. But if you use more shots, yeah, performance goes up, which is good. Yeah, so in this case, they check that model needs more loops in the architecture when the problem is complex, let's say. So it's for example, high school mathematics needs 5 loops, but logical or moral scenarios need much more, let's say 20 or 25.
Yeah,
Yeah.
some of the inference time loops are kind of interesting. So RJ asked about the recurrent backprop. So they have this little section here in chapter 4 on truncated backprop, where I think they truncate everything except for like the last 8 or
Yeah.
something. And then so what that allows is you can still have somewhat efficient training, but at inference time, the thing can still like roll out its internal thought for as long as it wants. But they have a little section somewhere. I think it's in chapter section 4 on truncated backprop. But efficiency training wise, that helps.
Right, but for like if you
Right.
I think it was saying like they truncated it like eight loops or whatever. But doesn't that mean that like for those 8 loops you can't parallelize, right? Like you have to do one after another.
Yeah, I think.
Which I mean I understand if you truncated it some number, then you're limiting the impact of that, but still uh that will I don't but I'd be curious to see like the impact overall of those layers that are recurrent. What's the impact on the training efficiency or speed?
Yeah, it was the 8. Is there any question or my internet?
Oh, sorry. When people join, they're just unmuted, so
Oh,
unmute.
okay.
Okay.
Yeah.
There is another question in chat though. How does it choose the depth? Would it make sense to recur until a stop token slash signal is output? Do you want to kind of explain what this internal thinking is doing and how it works?
So actually in the training, they took some random numbers. I'm not sure why they did that, because actually it can be learnable parameter, because you don't know the complexity of the data, right? So you cannot say the exact number of the loops in the pre-training. But yeah, actually it works, and yeah, I'm not sure. Yeah, as I mentioned, the recurrent work is not the novel idea. We know a lot of papers which did the same kind of things. But yeah, as I mentioned, some ideas should be rediscovered sometimes. So yeah, but I like that idea, especially for small models when you don't have a lot of context size. And yeah, that's interesting at least. So
I think at a high level as well, we have to remember what they're doing, right? They're training a 3B from scratch on 800 billion samples, billion samples. It's very proof of concept, right? So there is ways where you can synchronize recurrent depth and parallelize this stuff, but this is more so the proof of concept to show that this works and if we should scale it up. The other thing we've seen with a lot of recurrent networks and state models is you can do conversions. So even if they're not peak efficient, you can convert Quen to this style by, replacing layers and adding stuff. So all optimization stuff kind of comes a little bit later, but there is stuff like this I know in CUDA, but they probably got some AMD compute sponsorship to train this on MI300Xs, which is cool. Now, I don't know if they would write all that in the paper because it's not applicable for everyone, but just that's a little bit of it high level too.
yeah. Mhm. Okay, any other questions or comments? Actually, they mentioned that it's equivalent to 50 billion, but I can't see that in the results, because in the result they compare only for all models, which is 7B. Okay, I think that's it. Yeah, there was a lot of other sections, but I think the idea was to create a different technique rather than explicitly generate the output token, which is interesting at least, and a different kind of architecture. So I think it worth to test. Maybe we'll see the other paper that will do the same. So that's why I like that paper, just to understand other kind of techniques rather than the generation and so on. So,
Awesome.
yeah.
Cool. Thank you so much for volunteering to present. Do we have any other questions on these two? We still have a little bit of time. So scaling up test time compute was more so how we do internal reasoning. If we don't want to externally spit out this reasoning, can we have a recurrent state piece in our model? That's kind of what recurrent networks used to do. Can we train this to internally think? And then S1 was basically, can we get really good sample efficiency for reasoning tokens? And
Yeah.
both of these show pretty good promise.
Yeah, actually, this is pretty different, but yeah, the idea is the same. Okay. How does it decide to stop iteration on a token? In the inference, right? I'm not sure actually. Maybe you control the loop, not it doesn't decide itself.
No, I think it does because if you look on page 31, there's in the appendix, there's one of these heat maps. And it shows that for different tokens, it's inferencing for different numbers of steps. Yeah.
For different tokens.
Yeah, so basically it's trained to keep doing this, but we only backprop on 8 steps, but that doesn't mean that it can't unroll the amount of iterations it wants to do. It's internal in the model.
Or maybe I'm reading this wrong. Maybe this is 64 steps and it's just, oh yeah, this is the log. This like the convergence time. Oh yeah, okay. So this is so maybe it does, you just do configure it to reason for a certain number of steps and whatever that is. Yeah, that makes more sense. Okay, got it.
Um,
Okay. Very, very cool papers. Pretty interesting to see other reasoning stuff. So we have a few more minutes. Anything else anyone wants to bring up, or should we talk about next week's paper? Okay, well we'll end a little early and go straight into next week's stuff. Thank you so much for presenting, by the way. We always like volunteers. If anyone wants to
for listening.
volunteer, I think next week I'm doing one, and the week after we should have an opening. So if there's anything interesting anyone wants to do, feel free to, volunteer and then we can get that worked out. But yeah, thank you so much for presenting.
Thank
Also,
you
pretty
for
last minute, we kind of switched up papers. So sorry for people that didn't get a chance to pre-read. It's always nice to be able to pop in, but you always get most value if you do some basic pre-reading, come with your questions, and then we can discuss them. So that's kind of the whole point of it. For next week, Hugging Face put out this pre-training guide. So it's kind of everything about scaling up LLMs, and they go very in depth. So it's a very long one. I'm hoping we can get it done in an hour. But it starts with how do we train on one GPU, multiple GPUs, um, how do we do MOEs, like what is training configs, basically everything you would want to know about training and scaling up models. So I will go through this and condense it down to what's a TLDR of this probably like 8-hour reading. How can we condense this down into like, high level overview, 45 minutes of chat, and then 5 minutes of Q&A. But very, very good resource. I will share it back in Zoom. Um, I think, come prepared and just read over the sections you find interesting. If you have any questions, come with questions. I'm sure this will be one where Zoom chat will be very, very active since it's basically a book. But that's the paper for next week.
yeah, I started reading, but it's a huge.
It's huge. It's huge. Thomas Wolfe, the one of the co-founders at Hugging Face, apparently he also did a walkthrough on YouTube. So if you guys like side content, want to listen to it, there's a YouTube version where he goes through this for quite a while. But yeah, next week, maybe just brush up on that. I'll try to have something in an hour that we can go through, and then it'll be good for Q&A. We'll have about like 100 people here that are all somewhat versed on the topic. But yeah, cool. Thanks everyone.
Yeah, Ron, thank
Thank
you.
you.
Take care.
Bye.